The theory of prehistoric cosmic detonation is generally acknowledged by most researchers as the essential clarification for the starting points of the universe enveloping the production of stars, planets, and all life in that, including us. Notwithstanding its fairly unconventional name, the term huge explosion appropriately catches the immensity of the occasion. At first, the universe was a thick assortment of particles, pressed into a space more modest than a pinhead from this minute point. An enormous blast of matter happened known as the huge explosion. This concisely sums up the interaction that unfurled over billions of years. However, regardless of the persevering fame of the theory of how things came to be, progressions in logical information have progressively tested its predictions. When NASA sent off the James Webb Space Telescope, the biggest and most developed space observatory to date, scientists guessed that its perceptions would reinforce the theory of prehistoric cosmic detonation. Unfortunately, after only 1 year in space, the telescope has dumbfounded researchers with its momentous capacities, giving extraordinary looks into the universes past. The James Webb Telescope's disclosures have revealed systems so old that they might actually reshape how we interpret the universe's origins. This unexpected disclosure has started intense interest among researchers and fans alike. One such noteworthy disclosure came when stargazer Rohan Natu, breaking down early pictures from the James Webb Telescope, coincidentally found a system that surprised everyone. This universe, named Glass Z13, seemed mysteriously gigantic and traced all the way back to only a short time after the enormous detonation, making it older than any previously noticed world. Nat's energy was tangible as he imparted the revelation to partners on the planet, depicting it as beyond anything astronomers could ever imagine. The James Webb Telescope, positioned far from natural impedance and furnished with state-of-the-art innovation, was intended to dive into the universe's earliest age, known as grandiose sunrise. This period, covered in mystery, denotes the formation of the universe's most memorable stars and worlds. By examining systems from this period, researchers desired to refine how they interpret major inestimable cycles like the impact of matter and dark energy. Initial assumptions for the James Webb Telescope's discoveries were humble, expecting a couple of weak, far-off universes. However, the truth surpassed all projections. The telescope's pictures uncovered systems of amazing development, testing existing models and provoking a whirlwind of examination. As researchers keep on dissecting the James Webb Telescope's information, the ramifications of these revelations could be significant, introducing a new era of cosmological comprehension. The surprising disclosures from this noteworthy observatory offer a tempting look into the universe's past, driving humanity's journey to unravel the secrets of existence. As early systems materialized, scholars and spectators ended up in a scramble to make sense of them. Might this gathering of oddly enormous and bright early worlds ever be fanciful, perhaps due to flaws in the examination of the telescope's initial perceptions, or if authentic, might they ever somehow be accommodated with standard cosmological models? Quite possibly were they the main means that the universe is stranger and more complex than our boldest speculations had assumed. In question isn't anything less than how we might interpret how the precise universe we know arose out of early-stage confusion. The early disclosures from the James Webb Space Telescope can possibly revise the initial parts of grandiose history. These sections concern far-off ages in distant systems, as well as our own presence here in the natural, smooth manner. As Mark McCarran, a senior counsel for science and investigation at the European Space Office involved with JWST, commented, "You build these machines not to affirm the worldview, but to break it. You just don't have the foggiest idea how it will break." In a way, JWST perceptions of RLY universes have been billions of years truly taking shape. Nonetheless, more unobtrusively, they trace back to the Space Telescope Science Foundation in 1985. Around then, the Hubble Space Telescope was as yet 5 years from send-off. However, the establishment's then chief, Ricardo Juan, requested that his group begin contemplating what might come after Hubble. A lot further away, regardless of initial fights about zeroing in on Hubble, Juan was tenacious, predicting the extensive development process. Guy Linger, then deputy overseer of SD Sky, alongside a little group, started drafting thoughts for what in the end turned into the cutting-edge space telescope, later renamed JWST. They perceived that while Hubble would be groundbreaking, its capabilities would be restricted by its pertions in noticeable light. The NGST then again would see in the infrared range, permitting it to enter further into the universe. The need for JWST turned out to be much more obvious in December 1995, when cosmologists directed the Hubble Deep Field Perception in spite of assumptions for finding a couple of faint cosmic systems. The subsequent picture uncovered a huge number of worlds extending back more than 12 billion years into the universe's set of experiences. After over 20 years of improvement, and at an expense of around $1 billion, JWST at long last sent off on Christmas Day 2021, the telescope went through thorough testing prior to arriving at its profound space objective a month after the fact. By July 2022, it was prepared to begin its hotly anticipated first year of science perceptions, known as Cycle 1. Some portion of JWST initial mission was given to high-influence programs including the Astronomical Evolution Early Release Science Survey and the GRIS Focal Point Amplified Overview from Space, both pointed toward revealing insight into the secrets of the early universe as stargazers openly gave endless hours to scanning separate patches of the sky looking for early universe cosmic systems. They at first expected modest discoveries similar to a more detailed variant of the Hubble Deep Field. In any case, they were in for a shock. Stephen Finlin from the College of Texas at Austin, driving the SE project, makes sense of that. Very far-off systems were supposed to arise solely after numerous information cycles from different projects. However, to cosmologists wonder these universes showed up very quickly. Previously, the record for the most far-off known system had a place with GNZ 11 seen in 2015 with a redshift of 11. Redshift estimates the expanding of light because of the universe's development with a higher worth, demonstrating more prominent distance. Yet from the very beginning of glass perceptions, two separate groups, including one drove by Rohan Natu, freely recognized glass Z13 with a redshift of 13, driving the enormous timetable back significantly further in their scramble for quick results. Specialists depended on worked on techniques for redshift assessment based on splendor estimations as opposed to additional time series direct estimations. In spite of their effortlessness, these evaluations uncovered worlds suddenly brilliant, iant, and enormous, some previously flaunting a heavenly man equaling a billion suns, much the same as our own smooth way, which is billions of years more experienced. The energy didn't stop there. In the resulting days, numerous universe competitors from soothsayers and glass arose, some with redshift gauges as high as 20, demonstrating they existed only a short time after the enormous detonation. These worlds showed circle-like designs not expected in such early astronomical ages. Furthermore, another group found proof of smooth waste systems at a redshift of 10, under 500 million years after the enormous detonation. Such fast rise of sizable universes challenges the expectations of the standard cosmological model lambda cold dark matter. To grasp this oddity, a brief return to early universe elements is fundamental. In the underlying minutes after the enormous detonation, the universe was a hot, thick soup of early-stage particles over the long haul. As the universe extended and cooled, helium and other light components framed, prompting the presence of the principal iotas around 400,000 years after the fact, approximately 100 million years after the enormous detonation. Conditions became helpful for the development of the principal stars, made essentially out of hydrogen and helium. These early stars, bigger and more splendid than current stars, amassed into proto-worlds directed by the gravitational draw of dim matter. However, JWW's revelation challenges this model, as it uncovers splendid, sizable cosmic systems far sooner than anticipated. Stacey Core from Case Western Safe College noticed the startling shortfall of various more modest protogalactic parts, suggesting that some noticed systems might be nearer than assumed, hidden by dust seeming dimmer and more far off. The disclosure of the early worlds brings up significant issues about the universe's early stages, highlighting the need for proceeded with investigation and amendment of our cosmological models. Follow-up perceptions of glass Z13 in August 2022 by the Odom, a huge millimeter exhibit in Chile, cast uncertainty on the underlying discoveries regardless of the utilization of brilliance-based estimations. ALMA didn't recognize critical measures of residue associated with glass Z13, as P. Tom B. from Goya College, who drove the perceptions. This recommends that low redshift intruders can be excluded. However, ALMA attempted to recognize the universe by any means. This highlights the test of affirming perceptions made utilizing JWST HIO capabilities. Rohan Nadu, one of the specialists in question, brought up the incongruity of the circumstance, expressing the uplifting news is there's nothing identified. He said the terrible news is there's nothing identified to just JWST fit for circling back to its own perceptions. The most frightening clarification could be that the standard LCCDM cosmological model requires updating. Michael Bohan Cullen, a cosmologist, communicated the size of this potential change in outlook, expressing these outcomes are extremely astonishing and difficult to get in our standard model of cosmology. It would be a genuine insurgency to comprehend the quandary. One questionable proposition is change Newtonian elements, which challenges the existence of dark matter. JWST perceptions could lend backing to MZ proposed by Mark McCarran. However, not all cosmologists are persuaded of MZ's validity. Another conceivable explanation is that early universe worlds might have almost no residue, causing them to seem more splendid and influencing mass computations. The situation could likewise make sense of ALMA's difficulty in recognizing glass Z13. Charlotte Brickley and her associates proposed that JWST could be noticing the most splendid youthful systems in the early universe, which could suggest simpler star formation conditions during that age. David Spergel upholds this thought, proposing that high-mass star development could have been more proficient because of higher gas tensions and temperatures conceivably influenced by early attraction fields. The quick dispersal of logical papers from JWST initial perceptions mirrors a shift towards ongoing companion survey via stages like F14 in virtual entertainment. While this speeds up the scattering of discoveries, there are worries about hurrying ends. Before intensive companion survey, notwithstanding alignment issues and potential recalibrations influencing a few outcomes, it's impossible that all high redshift cosmic systems saw by JWST will be nullified. All things considered, the sheer number of these worlds recommends that the early universe might be not the same as what was previously anticipated. Finland communicated trust in the legitimacy of the disclosures, expressing that the chances of cosmologists being altogether base are small. Presently, stargazers are hurrying to direct subsequent perceptions with JWST. Nancy Levinson is right now evaluating around 12 recommendations from different gatherings, looking for extra JWST noticing time, for the most part to examine high redshift cosmic system up-and-comers. Given the energy and meaning of these early disclosures, affirming them is vital. Try, who presented one of the recommendations, underscored the significance of affirming these discoveries. Different projects like Cosmos Webb drove by Cartel T expected to expand the known populace of early systems by noticing a more extensive region of the sky for many hours. Fundamentally, they appraised that they might identify great many systems. Besides, extra undertakings will look for proof of the main proto-universes, conceivably utilizing the unstable passings of supersized first stars and radiant cosmic explosion as markers for their reality. A few evaluations recommend that JWST could notice cosmic systems to the extent a red shift of 26, only 120 million years after the enormous detonation, affirming even a small bunch of these high red shift up-and-comers would be a wonderful accomplishment, as indicated by Natu, showing that cosmologists are not being deluded by their perceptions. JWST has presented another period of science, and regardless of the vulnerabilities, the rapid correspondence of new re-ation has stimulated stargazers. TRO expressed energy about the associated with an invigorated academic local area. Presently, the inquiry emerges as now is the right time to reconsider how we might interpret the very beginning artisan pond, the significant ramifications of looking into the unexplored world that completes up the data. For now, remember to show your help by preferring buying and stirring things up around town for future episodes. Also, make certain to share your contemplations on the present substance. Your help rouses us to keep conveying quality substance and to constantly take a stab at progress. Gratitude for watching, and we'll see you sometime later. In conclusion, the James Webb Space Telescope JWST has ushered in a new era of exploration and discovery, challenging our understanding of the universe's origins and evolution. Its unprecedented observations of galaxies formed shortly after the Big Bang have sparked excitement and debate among scientists, pushing in the boundaries of cosmological knowledge. The telescope's ability to peer deeper into space and time than ever before has unveiled cosmic phenomena that defy conventional models, prompting a re-evaluation of existing theories and the formulation of new ones, from ancient galaxies to the mysteries of dark matter and early star formation. JWST findings have profound implications for our understanding of cosmic history. Looking forward, JWST promises to continue unraveling the universe's complexities, offering glimpses into epochs previously beyond our reach. Its discoveries not only advance scientific inquiry but also inspire wonder and curiosity about the universe's vastness and our place within it. As JWST embarks on its mission to further explore the cosmos, scientists eagerly anticipate what new revelations lie ahead. With each observation, we move closer to unraveling the fundamental questions of existence and gaining a deeper appreciation of the CA tapestry that surrounds us. In essence, the James Webb Space Telescope stands as a testament to human curiosity and ingenuity, driving us towards a deeper understanding of our cosmic origins and our place in the universe's grand narrative. The theory of the prehistoric cosmic detonation, known as the Big Bang, is widely accepted among researchers as the fundamental explanation for the origins of the universe. It encompasses the creation of stars, planets, and all life, including us. Despite its unconventional name, the term Big Bang aptly captures the immensity of the event. Initially, the universe was a dense collection of particles compressed into a space smaller than a pinhead. From this infinitesimal point, a massive explosion of matter occurred, known as the Big Bang. This succinctly summarizes the process that unfolded over billions of years. However, despite the enduring popularity of the Big Bang theory in explaining the origins of everything, advances in scientific knowledge have increasingly challenged its predictions. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory to date, Scientists anticipated that its observations would strengthen the theory of the Big Bang. Unfortunately, just 1 year into its mission, the telescope has confounded scientists with its remarkable capabilities, providing unprecedented glimpses into the universe's past. The JWST's discoveries have unveiled galaxies so ancient that they could potentially reshape our understanding of the universe's origins. This unexpected finding has sparked intense interest among scientists and enthusiasts alike. One notable discovery came when astronomer Rohan Naidu, analyzing early images from the JWST, serendipitously found a galaxy that astonished everyone. This galaxy, named Glash Z13, appeared unusually massive and dated back to just shortly after the Big Bang, making it older than any previously observed world. Naidu's excitement was palpable as he shared the revelation with colleagues, describing it as beyond anything astronomers had imagined. The James Webb Space Telescope, positioned far from earthly interference and equipped with state-of-the-art technology, was designed to delve into the universe's earliest epoch known as cosmic dawn. This period, shrouded in mystery, marks the formation of the universe's first significant stars and galaxies. By studying galaxies from this era, researchers aim to refine their understanding of major cosmic phenomena like the influence of matter and dark energy. Initial expectations for the JWST's discoveries were modest, anticipating a few faint distant galaxies. However, reality far exceeded projections. The telescope's images revealed galaxies of astonishing size and growth, challenging existing models and prompting a flurry of research. As scientists continue to analyze the JWST's data, the implications of these revelations could be profound, heralding a new era of cosmological understanding. The surprising findings from this groundbreaking observatory offer a tantalizing glimpse into the universe's past, propelling humanity's quest to unravel the mysteries of existence. As early galaxies materialized, scholars and spectators alike scrambled to make sense of them. Could this gathering of unusually massive and luminous early galaxies be real, or were they merely artifacts of flaws in the telescope's initial observations? If authentic, could they ever be reconciled with standard cosmological models? Quite possibly, they were indicating that the universe is stranger and more complex than our boldest speculations had assumed. Central to this question is nothing less than how precisely the universe we know emerged from its early chaotic state. The early discoveries from the James Webb Space Telescope have the potential to rewrite the opening chapters of cosmic history. These chapters cover remote epochs in distant galaxies as well as our own existence here on Earth. As Mark McCarran, a senior scientist at the European Space Agency involved with JWST, commented, "You build these machines not to confirm the worldview but to break it. You just don't know how it will break." In a way, JWST's observations of early galaxies have been billions of years in the making. Nonetheless, more subtly, they trace back to the Space Telescope Science Institute's inception in 1985. At that time, the Hubble Space Telescope was still 5 years away from launch. However, the Institute's then-director, Riccardo Giacconi, tasked Ed Weiler and his team to start contemplating what would come after Hubble. Despite initial struggles over focusing on Hubble, Giacconi was persistent. Driven by the vast potential, John Mather, then deputy director of STSCI, along with a small team, began drafting ideas that eventually became the Advanced Space Telescope, later renamed JWST. They recognized that while Hubble would be groundbreaking, its capabilities would be limited by its observations in visible light. The JWST, on the other hand, would operate in the infrared spectrum, allowing it to peer deeper into the universe. The necessity for JWST became even clearer in December 1995 when astronomers conducted the Hubble Deep Field observation. Despite expectations of finding a few faint galaxies, the resulting image revealed thousands of galaxies stretching back over 12 billion years into the universe's history.